Hello everyone, welcome back to Math 143 Finite Mathematics. So here are two additional simplex method examples with step-by-step solutions. This follows the same simplex method structure from section 4.1. The standard maximization form, slack variables, initial simplex tabulo, and pivot column, pivot row, and read in the optimal solution. Okay, let's say the first example. Example 1, which has two variable simplex problem. The problem: maximize p equals 3x plus 2y subject to the constraints x plus y less than or equal 4, x less than or equal 2, y less than or equal 3, and x greater than 0, y greater than or equal 0. Okay, let's solve this linear programming problem using the simplex method. First, notice that this is already a standard maximization problem. Because we have maximization problem, all the inequalities are less than or equal non-negative constant value and the non-negativity constraints are satisfied. So the objective function is being maximized here. You can see it again. All constraints use less than or equal to, less than or equal to, less than or equal to, less than or equal to a constant value, and both variables are non-negative. Okay, now as of the first step, we wanted to introduce the slack variables. Okay, let's introduce the slack variables. Step 1, add slack variables. Okay, x plus y plus s1 equals 4, x plus s2 equals 2, y plus s3 equals 3, and rewrite the objective function. So the objective function here, negative 3x, negative 2y plus b equals 0. Then let's write down the initial simplex tabulo. Next step, okay, we have x, y, s1, s2, s3 and p. X, y, s1, s2, s3, p. And the constant term. Then from the constraint 1, 1, 1, 0, 0, 0, 4. From second one, 1, 0, 0, 1, 0, 0, 2. Third one, 0, 1, 0, 0, 1, 0, 3. And the bottom line, which is the objective function, negative 3, negative 2, 0, 0, 0, 1, 0. So this would be the initial simplex tabulo. Then now look at the bottom row of the initial simplex tabulo. So look at the bottom row. So the most negative entry is -3, right? So the pivot column is the X column. The most negative entry is -3. So the pivot column is the X column. Next, now we compute the ratios using positive entries in the pivot column. So the ratios 4/1, 4, 2/1, 2, right? Next step. Pivot in. So ratios are 4/1, 4, 2/1, 2. The smallest positive ratio is 2. So the pivot row is R2, row 2, right? So the pivot row R2. Then the pivot element where both row and column intersect. So the pivot element is 1. So pivot element 1. Okay, then let's use the row operations, right? So we have X, Y, S1, S2, S3, P, and constant. One, 1, 1, 0, 0, 4, 1, 0, 0, 1, 0, 0, 2, 0, 1, 0, 0, 1, 0, 3, and end -3, -2, 0, 0, 0, 1, 0. Okay, the pivot entry here is this. Okay, so now we wanted to do the row operations to get all other entries in the pivot column equals 0. So R1 minus R2 goes to R1. Also, to remove this -3, 3 times R2 plus R4 goes to R4. Okay, 2 steps. Then X, Y, S1, S2, S3, P constant, right? So R1 minus R2, which removes this +1, 0, then 1 minus 0, 1, 1 minus 0, 1, 0 minus 1, -1, 0, 0, 4 minus 2, 2, right? Okay, then the second row remains unchanged, 1, 0, 0, 1, 0, 0, 2. Third row also remain unchanged because we don't need to consider the element in the third row. The first element in the third row is already 0. Next, then 3 times R2 plus R4, 0. It converts this -3 into 0. then -2, 0, 3, 0, 1, 6. Okay, then check for the bottom row again. The bottom row still has a negative entry, -2. So we are not finished, right? The bottom row still has a -2 in the negative entry, not finished, right? Therefore, we wanted to follow all the steps again. Now, the pivot column, let's use another color then. The pivot column, this, then take the ratios 2/1, 2, 3/1, because this is 0, we don't need to consider the second row. 3/1, 3. Then the new pivot row is row 1 and the new pivot entry 1 again. So step 4, second pivot, ratios 2/1, 2, 3/1, 3. Smallest positive ratio is 2. So pivot row is R1 and pivot element is 1. Then use row operations again. Okay, we have 0, 1, 1, -1, 0, 0, 2, 1, 0, 0, 1, 0, 0, 2, 0, 1, 0, 0, 1, 0, 3, and the bottom line 0, -2, 0, 3, 0, 1, 6. Okay, then let's do the row operations. Now the pivot entry is this. Then we wanted to remove this and this. So R3 minus R1 goes to R3. Also R4 plus 2 times R1 goes to R4. Okay. We have X, Y, S1, S2, S3, P constant. R1 remain unchanged. R2 remain unchanged because we have the pivot column entry 0 in R2. Okay, then we have third column, third row, R3 minus R1 goes to R3, 0, 0, -1, 1, 1. Okay, R3, 0, and And here we have 0, 0, 2, 1, 0, 1, and 10. Okay. Then look for the bottom line. All entries in the bottom row are non-negative, so the solution is optimal. So all entries in the bottom row are non-negative, so the solution is optimal. So then let's write down the solution using the unit column. We have the unit column here, x, that corresponding entry x equals 2, and what are the other unit columns? Here we have unit column y, the corresponding entry 2, then y equals 2. The unit column here is 3, the entry is 3 equals 1, and the last one we have the unit column p, the corresponding entry 10. All other entries, that means not the unit columns, then S1 equals 0, S2 equals 0. So this would be the optimal solution. The maximum p equals 10 at x equals 2, y equals 2, S3 equals 1, S1 equals 0, S2 equals 0. So that's it. Okay, then let's move into the one more example. So in this example, I am going to use 3 variable simplex problem. Example 2. Three variable. So maximize the objective function p equals 2x plus 3y plus 4c. Subject to the constraints x plus y plus c less than or equal 5, 2x plus y plus 3z less than or equal 12, x plus 2y plus z less than or equal 8, x, y, z all greater than or equal 0. Okay, now let's try a problem with 3 variables. This is where the simplex method becomes very useful, because graphing a 3 variable feasible region is very difficult. We will follow the same steps: add slack variable, write the initial simplex tabulo, choose the pivot column and pivot row, and continue until the bottom row has no negative entries. Okay, let's convert this into the standard maximization problem. Here we have all conditions satisfied. The maximize the objective function subject to the constraints are less than or equal constant value and the non-negativity satisfied. Then step 1, add slack variables. Okay, for the first one, x plus y plus z plus s1 equals 5. Second, 2x plus y plus 3z s2 equals 12. X plus 2y plus 2z plus s3 equals 8. An objective function. Then convert the objective function. Negative 2x, negative 3y, negative 4z plus p equals 0. Okay, then using this, step 1, let's obtain the initial simplex tabular. Step 2, initial simplex tabular. Okay, we have x, y, z, s1, s2, s3, p, and constant. From the first one, 1, 1, 1, 1, 0, 0, 0, 5. From the second one, 2, 1, 3, 0, 1, 0, 0, 12. Third one, 1, 2, 2, 0, 0, 1, 0, 8. And the objective function, negative 2, negative 3, negative 4, 0, 0, 0, 1, and 0. Okay, look at the bottom row. The most negative entry is negative 4. When we look in at the bottom row, the most negative entry is negative 4. So the pivot column is C column. And take the ratios. 5 over 1, 5, 12 over 3, 4, 8 over 2. Okay, I got the mistakes here, right? You should keep in touch. Yeah, it should be 1. Then the ratio 8 over 1. 8. The smallest ratio is 4. Therefore, the pivot row, the second row. And the pivot entry is 3. Okay, then apply the row operations. Until you get the non-negative values in the bottom line. So here I will perform some steps. After pivoting with few steps, we will get x, y, z, s1, s2, s3, p, and the constant 1/3, 2/3, 0, 1, negative 1/3, 0, 0, 1, 2/3, 1/3, 1, 0, 1/3, 0, 0, 4, 1/3, 5 over 3, 0, 0, negative 1/3, 1, 0, 1 0 4. On the bottom line we will have 2 third negative 5 over 3 0 0 4 over 3 0 1 and 16. Now check the bottom row again. So there is still one negative entry, negative 5 over 3. So we are not finished. Right. So the next pivot column is Y, and ratio 3 over 2, 3 over 4, 12 over 5. So the smallest positive ratio is 3 over 2. Then pivot row, row 1, new pivot column Y, new pivot row R1, pivot entry two over 3. Then after performing pivot again, after pivoting using row operations, we will have x, y, z, s1, s2, s3, p, and the constant term. So 1/2, 1, 0, negative 0, 0, 3 over 2, 1/2, 0, 1, 1/2, 0, 0, 7 over 2, negative 1/2, 0, 0, negative 5 over 2, 1 over 2, 1, 0, 3 over 2. The bottom line we have 3 over 2, 0, 0, 5 over 2, 1/2, 0, 1, 37 over 2. So the bottom row has no negative entries, so the solution is optimal. No negative entries, therefore the solution is optimal. So let's see the solution. The unit column Y and corresponding constant value, therefore Y equals 3 over 2. The unit column Z corresponding value, then Z equals 7 over 2. And unit column S3, the corresponding value 3 over 2. The unit column P, corresponding value P equals 37 over 2. So the optimal maximum value of P is 37 over 2, that means 18.5, and which is at Y equals 3 over 2, Z equals 7 over 2, S3 equals 3 over 2, then X equals 0, X x equals 0, s1 equals 0, and s2 equals 0. Okay, so you can check the pivoting using row operations, that you can use row operations to convert until get the optimal solution. So let's summarize what we did in these examples. So for each simplex problem, we followed the same process. First, we checked that the problem was in standard maximization form. Second, we introduced slack variables. Third, we wrote the initial simplex tabulo. Fourth, we selected the pivot column by choosing the most negative entry in the bottom row. Fifth, we selected the pivot row using the smallest positive ratio. Then we pivoted until all entries in the bottom row were non-negative. At that point, the tabula was optimal. Finally, we read the solution by identifying the basic variables and their values from the right-hand side column. So remember, the simplex method is just an algebraic way of moving from one corner point to another until we reach the best possible solution. Okay, so the simplex method is done. So if you have any question, feel free to reach me out. So then let's move for the chapter 5. Thanks for watching.